This is lesson 2.6, Applications of Matrices. It's also our last lesson for chapter 2. We're going to go through two applications today, and I'm really excited about both of these. I'll be honest, this first one actually kind of blew my mind. It's one of those things that I either just never learned or had completely forgotten about. And it involves least squares regression lines, or finding the line of best fit. Now, maybe like your experience, whenever I've found linear regression, whenever I've done a linear regression problem to find that line of best fit, I've always done it using technology. You put in the values, you put in the ordered pairs, and then you just find the linear regression, let the calculator or computer do the work for me. But today we're going to look at how do we use matrices to actually do that process. In other words, this is really what's happening behind the scenes in the programming of that calculator or computer to find the least squares regression line. And I would actually encourage you, when we're done with this example, if you've got the technology to do this, again, a graphing calculator or a computer program that can do this, plug these numbers in and actually do the linear regression with technology to see that you will get the same answer that way as we do here. So pretty cool with this. And then the second example that we'll do actually involves cryptography, which is also a really cool application. And again, just starts to open, I think, the idea of just some of the things that mathematics does, beyond just, some of the ordinary things that we might typically think about doing. So let's go ahead and let's start with this first one. So we have 5 points here. And again, if we were to graph these, we would see that they were generally in a line, but not quite, not perfectly so. And we are simply going to find the line of best fit, that line that would best fit that data. So as we get into this, let's just think about what this is going to look like. So it's linear. So we're going to be looking for something that has kind of this form to it, where again, a sub 0 is our y-intercept, a sub 1 is the slope of the line. And so another way to think about this then is what we're going to be doing is ultimately trying to find a matrix that is going to give us those two values. We're going to look for a 2x1 matrix where the first entry is going to be the y-intercept. The second entry is going to be the slope. And the way that we're going to find this, I'll kind of give you the whole big formula, if you will, and then we're going to break this down into pieces and do this. But what we're going to do is we're going to take, we're going to set up some two matrices. We'll call one x, we'll call one y. We're going to take the transpose of x times x, and then we're going to take the inverse of that, and then we're going to multiply that by the transpose of x times the matrix of y. So we're going to kind of do this in two parts. We're going to find this part first, and then we're going to find this part, and we're going to multiply those two things together. And the result of that is going to be a 2x1 matrix that has our y-intercept and our slope. And it doesn't matter how many points you have. You can do this with 2 or 3 points. You can do this with 100 points. Obviously, the more points you have, the lot more work it's going to be to do this with matrices. But the number of points does not matter. This will work every time and always bring you down to that 2x1 matrix. So we've got our points, 1, 1, 2, 3, 3, 5, 4, 6, and 5, 10. And we are going to put those into two matrices, like I said. So the first matrix that we're going to create is the X matrix. And this matrix is always 2 columns. Obviously, the number of rows is just based on how many points you have. And the first column is just always ones. So in this case, we have 5 points. We'll have a column of 5 ones. The second column are all of the x values from our points. Now, obviously, the key here is we do have to keep these in order. Not necessarily in order within this matrix, but when we create our second matrix, order of the points is important. So in this case, if I'm going to just go from in the order listed, the x values are 1, 2, 3, 4, and 5. So that's the first matrix, column of ones, column of your x values. The second matrix is going to be y, and this is simply a 1-column matrix. And this is going to be all of our y values. So this is where it's important on that order, right? So I don't have to put my x values in the order 1, 2, 3, 4, 5. I just have to make sure that the y values are in the same order as the x values. So in this case, The y values are 1, 3, 5, 6, and 10. Okay, so that's how you create the two matrices. One with the x values, one with the y values. And now we're going to just go ahead and start breaking down this formula, finding those different pieces, putting it all together to get that final answer. So starting with the first part, we're going to find x, the transpose of x times x. So the transpose of x, remember we just put it into rows. So 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5. And then we're going to multiply that by the matrix X. All right, so this is going to give us, let's see, well, the first entry is easy. The first entry is going to be just 1 plus 1 plus 1 plus 1 plus 1, or 5. Then we've got 1 plus 2 plus 3 plus 4 plus 5, which is going to be 15. And then the third entry, the second row, first column, is just 1, 2, 3, 4, 5 times 1. So that's also going to be 15. And then this last one, that's going to take a little more thought here. We've got 1 plus 4 plus 9 plus 16 plus 25 is, I believe, 55. All right. So that's the first part. Now we're going to take the inverse. I guess we can do the inverse now, or we can do it later, I suppose. Maybe I'll do it later. Maybe I'll do this kind of in one less step here. Let's go ahead and find the transpose of x times y. We'll do that next. I think this will work out pretty well. So the transpose of x, that's obviously still the same as what we just had before. And now we're just multiplying that by y, that single column matrix, 1, 3, 5, 6, 10. So in this case, we're just going to have a 2 by 1 matrix. So we'll have, in essence, 1 plus 3 plus 5 plus 6 plus 10, which is 25. And then 1 plus 6 plus 15 plus 24 plus 50 is 96. All right. So we have everything really except for the inverse of that first matrix that we found. But I think we can do this all kind of in one fell swoop. I think I'm going to go right to the end here. Because if we do it this way, oops, this should work out for us. So we've got this inner part, right? This matrix 5, 15, 15, 55. But we want the inverse of that. So we're going to flip that around. So 55, 5, negative 15, negative 15. And then I just need that determinant. I just need that number in front. So if I multiply the diagonals and subtract, we've got, let's see, 275 minus 225 is 50. So we'll have 1 over 50 here. So this whole part represents xt, x to the negative 1. Okay. So that's going to be that whole first part. So it's taking the inverse, multiplying by the determinant, and then we're going to multiply that by the 2596. Okay. Now at this point, quite honestly, because remember, ultimately what we're looking for is the equation of a line. I would probably just like run these numbers through the calculator. We're not going to worry about exact answers over 50 or things like that. Oops, there shouldn't be a line there. It should just be 2596. So I would just plug this into the calculator. Just 55 times 25 plus negative 15 times 96. Get that answer, divide by 50. And then do the same for the second row. Negative 15 times 25 plus 5 times 96. Get that answer, divide by 50. And if you do that, you get a resulting vector, or matrix, of negative 1.3 and positive 2.1. Now remember that this matrix is x0, x1, where x0 is our y-intercept and x1 is our slope. So the equation for our line of best fit, our least squares regression line, is simply negative 1.3 plus 2.1x. So as I mentioned earlier, I'd encourage you, if you've got the technology to do this, go ahead and plug those five numbers in. You'll make your lists and do that linear regression using technology, and you will find that you get the exact same answer, because this is the algorithm that the technology is using to find that line of best fit. So I think that's pretty cool. Like I said, something that either I'd never learned or I'd completely forgotten about. When I came across this guy, I was like, oh, that's so cool. All right, nerding out on you a little bit here. All right, let's go ahead and let's look at the second example then, which is cryptography. So obviously, cryptography in terms of secret messaging and things like that is incredibly important. Certainly, as when we think about some of our world wars and breaking some of the codes and what that did to turn the tide of the war, some pretty important stuff. So what we're going to do is obviously look at a fairly simplistic example here, but an example that uses matrices to decode and encode messages. And so we're going to take a really simple message here, Friday, 8 p.m., and we're going to encode the message, first of all, and then show how we would, send that message, and then on the other side, the other end of that, the recipient would then decode that message back into something that makes sense. So I'm not going to get into a lot of the detail. We're just going to kind of allow the example to show the process. So basically what we're going to do is we have to start by assigning numeric values to each of the letters. So assign numeric values to each letter. Or I guess a numeric value to each letter. And we're gonna just use A as 1, B as 2, C as 3. So we're just going to use that kind of very typical normal way. And then we're going to use 0 for spaces, because we do want to account for spaces here. We wouldn't have to necessarily, but it certainly makes it a lot easier for the decoder on the other end to not have to worry about figuring out where the breaks are in the different words. So in this case then, if I take this this message, Friday, 8 p.m. I should have left a little more space before I'm going to just give myself a little more space here for the actual space itself. So assigning letters, F is going to be 6, R is 18, I is 9, D is 4, A is 1. By the way, if you're wondering how I might be doing this, there is actually a chart in your book that has all of the letters with the assigned numbers to them, or you can just find it elsewhere. We technically have a space here. I'm going to put 0 there, and then we've got 5 for E, 9 for I, GH 7, 8, T is 20. We've got another space here for 0, P is 16, and M is 13. So we've assigned all of the numbers, and now what we're going to do is we're going to basically use an invertible matrix to encode this. So obviously the matrix that we use has to have an inverse, because on the other end, that's what they're going to use to decode it. So we're going to use a matrix to encode. They'll use the inverse matrix to decode it. So we're going to use an invertible matrix. To encode the message. Now, how we do this and everything is really arbitrary. It's just a matter of the system that you would decide to set up. In this case, if we count up the number of characters, including the spaces, we have 15 total characters. So we could, if we wanted to, break this up into blocks of 5 or blocks of 3. I'm going to use blocks of 3 because the number of blocks, the size of your block determines the size of your matrix. So I could, for example, chunk this out into groups of 5 numbers, but then I would need to use a 5 by 5 matrix to encode and decode it, which is fine. But I think for our purposes, we're going to make this a little easier for ourselves. So I'm going to block this into groups of 3. So what I'm going to do is I'm going to take those numbers and basically make these row matrices in groups of 3. And now I'm going to take a 3 by 3 matrix. So I'm going to take a matrix. I've already kind of played around with this and found one that actually works nicely. I didn't want an inverse matrix with a bunch of fractions and things like that. This one actually works nicely to give us some integers when we do the decoding side of this. But that's the matrix we're going to use to encode the message. And what we do is we simply take each of these 3-character blocks or 3-entry blocks that we made, and we're going to multiply it by A. So I'm going to take 6, 18, 9, and I'm going to multiply it by that matrix A, the 1, 2, 2, 3, 7, 9, -1, -4, -7. And again, because I am multiplying a 1 by 3 and a 3 by 3, the result is going to be another 1 by 3 matrix. So when I multiply these together, and I'm just gonna I did this in advance, so I'm just gonna run through these numbers for you. This is the matrix that we get when we multiply these together. Okay. So in other words, the 51, the 102, the 111 correspond back to the 6, 18, and 9. Obviously, though, 51, 102, 111 mean nothing to somebody who's just seeing those numbers. Okay. And you know, as you think about this, you know, if I send a message with those numbers, how would you get it back to 6, 18, 9 is a real challenge, because there's an infinite number of matrices that could have been used to encode. You also then have to take the inverse of that correct matrix to decode it. So you can start to see, and this is a very simplistic way of encrypting, but you can start to see where it would be very, very difficult if we use larger matrices, if we use other algorithms within this process. We can do things to even mix this up even further. You can create some systems and some algorithms that get very, very complicated very fast and make decryption a very, very difficult thing. So then we keep going, and I'm not going to rewrite the large matrix over and over again here, but if I take the other numbers, the other blocks, if you will, I'm just going to rewrite those blocks so we can kind of see how they match up. 7, 8, and 20, and then our last one is 0, 16, and 13. So again, if I just carry this matrix all the way down and just multiply each of these, what I get then are the matrices -18, -85, and -158. And then 6, -1, -18. Sorry, my brackets. My brackets are really sloppy. And then we get 11, -10, and -54. And then finally 35, 60, and 53. Okay. So obviously the left side, what we started with, the right side, what we've encoded them to. So the message that I would actually send then, I wouldn't send them in blocks of 3 like this, because that's going to give away some information about how to decode this. I would just simply send the numbers 51, 102, 111, -18, -85, and so on. I won't write them all down, but I would just literally send this list of numbers in order. So on the other end, to decode this, they would have to know a couple of different things. They would have to know the matrix or its inverse to decode it. And they would also need to know how to break this apart. Now, obviously, if it's a 3 by 3 matrix, you're going to break it apart in groups of 3. But without those 2 pieces of information, you wouldn't be able to decode this. So the idea now is on the other end to decode this. And I'm not going to go through the whole process here. I'm just going to go through just one step of this, because then it's just repetition to get the rest of it. But so we're going to need the inverse matrix. So if I take A and I find its inverse, the result is -13, 6, 4, 12, -5, -3, and -5, 2, 1. So now, just like we did before, where we multiplied each of those blocks times matrix A to get the encoded numbers, Now I'm going to take each of those blocks times the inverse of A to get the decoded. So I'm going to take this first block, 51, 102, 111. 51, 102, 111. And I'm going to multiply that by the inverse of A. And when I do that, I will get what I started with, the 6, 18, 9. So it's going to revert it back to that first string of the message. And obviously, if we did this 4 more times, did all of the different blocks, we'd have all the numbers. We simply translate them back into letters, and now we've got the message Friday, 8 p.m. So again, this is not, as complicated as this would be for kind of most people to decode, or try to break the code. When you think about using computers and such to try and break codes, and the millions of steps that a computer can do to try and work out the correct algorithm, this is fairly simplistic still. But again, you can imagine the complexities that we can put on top of this to make it even more secure and even more difficult to break that code. So that's how just we can use matrices, though, to create those coded messages to use in cryptography like this. So that's it for this lesson. And again, this ends chapter 2, and I will see you in the next chapter.